I'm going to demonstrate the numerical integration that we went over in the first tutorial. That's the one where these kids were jumping off the bridge, and after the bungee cord goes tight, they become a particle acted upon by gravity and a spring force. And we wrote Newton's law after drawing the free body diagram. And Newton's law gave us an equation of motion that related the acceleration and the distance they had fallen, where y was positive downward. We rewrote that acceleration equation as two first-order ordinary differential equations. So we're going to begin the simulation after they've fallen 80 feet. That's when the cord begins to bring up. And at that point, they have a free fall velocity of 71.8 feet per second. That's about to decrease because the spring's pulling up on them. So here are the two equations of motion and the initial values. What these equations tell you is that if you know your position and your velocity, then you can calculate the slope of the position versus time curve, and you can calculate the slope of the velocity versus time curve. And numerical integration means if we know our current value and if we know the slope of that value, then we can march forward in time along that slope direction, and we'll end up on the correct path. On page 3, I showed a hypothetical acceleration versus time curve. If I want to know the velocity, it starts off at some value v naught, and if I have positive acceleration, then the velocity is going to get bigger. The new velocity is going to be the old velocity plus the slope of the velocity curve times delta t. Slope times delta t is the area under this little rectangular portion of the acceleration curve. So if you integrate acceleration versus time, then you get the amount that you've got to add on to your initial velocity as you go forward in time. If you know your velocity, then your new position is going to be your old position plus velocity times time. So after each time step, new velocity is old velocity plus slope times time step, where the slope of velocity is acceleration. New position is going to be old position plus position curve slope times time step, where position curve slope is velocity. So on our Microsoft Excel sheet, I've just cut and pasted this equation box here. These are the two equations we are trying to numerically integrate. So we're going to start off with initial conditions. Our initial value of velocity is going to be, we said 71.6, and our initial value of the position was 80. And these things should be in feet and not meters per second. So I'll try to change that while eating up valuable bandwidth. Okay, so there's feet. And now we need to define our time values. Alright, let's start off at time 0. And then let's choose a time step. We'll choose a small time step, 0.1. And if I highlight both of those and I click and drag on the lower right portion of that box, I see my big fat cross turns into a thin cross, and I can drag that down, and I'll just keep adding time values with that 0.1 second separation. Alright. Now let's see, my initial value of y is going to be equal to 80. My initial value of velocity is going to be equal to what I put in that 71.6 cell. Okay, so my initial y is equal to that. My initial v is equal to that. Return. My initial acceleration, or v dot, that comes from my second equation of motion. That's going to equal minus 8.58 times position. What's position? Position is what's in this cell. Plus 718.9. Plus 718.9. Return. Okay, there's our initial acceleration. And oh, by the way, that's approximately equal to the free fall acceleration g in feet per second squared. Okay, so the next thing we have to do is figure out what's our new value of velocity after we've gone one time step. Well, that's going to be equal to our old value plus slope, which is acceleration or v dot, times delta t, which is going to be, in this spreadsheet, a10 minus a9. So I'll sum in a bracket here. That cell minus that cell. Okay, new value is old value plus slope times delta t. That ought to do it. So the velocity has gotten a little bit bigger in that one time step. We're still accelerating under free fall. There's not a lot of spring force built up yet, so it's not shocking that the velocity is still increasing. Our new position is going to equal our old position plus our slope, which is our previous velocity, times delta t, which is that cell minus that cell. Once again, okay, hit return. We've gone 7 feet in that brief amount of time. Now for v dot, now that we've got new y and new v, we can find a new value of the acceleration. So I'm going to copy that cell, Control C, and I'm going to paste it right there. Okay, so now this cell says that the acceleration is minus 8.58 times b10 plus 718.9. The next thing I'll do is I will copy and paste those 3 rows. Okay. Now what do I have? I have a whole bunch of time values, y values, velocity values, and acceleration values. I was interested in how far they'd fallen when the velocity had gone to 0. So really I'm only interested in the first half a second of this curve. So let's see, if I look at my Excel sheet here, v goes to 0 after about 0.6 seconds. So I'm just going to chop off all these values. Okay, we'll delete those. Delete. Okay, now I look at my curve for velocity. So by the time velocity gets to 0, I've reached a maximum vertical downward displacement of, looks like about 115 feet. So they haven't hit the water by the time they stop. So if we were going to solve this problem as asked on the problem statement, we'd have to go back and use trial and error, find a new unstretched spring length that was a little longer than 80 feet, and keep doing this until y maxed out at 120. Our time step seems fine because our curves are nice and smooth. Suppose I were to use a ridiculous time step like 1 second. So now in 10 or 11 steps we're going to go 9 seconds. Look what happens now to our curve. Things start going haywire, and we're so far off the curve because we took big time steps that these results are basically meaningless. So let's go back to our 0.1 second time step. We get reasonable looking results. I'm going to chop that time step in half. Actually, I'll chop it by a factor of 10. And if the results don't change, then that means my time step was good enough. I know I want to go for about 0.6 seconds, so if I've got a 0.01 second time step, I'll need to have a lot more of these columns. 10 times as many. Okay, so I'll drag down to there. will go back up to the top. I will do a copy and a paste all the way down past 0.6. And I get a curve that looks like the ones I had before. So I guess my 0.1 time step was fine. Refining the time step didn't give me any appreciable benefit. Okay, so setting the time step, just set it to the biggest possible value so that you get nice smooth results. And check it by shrinking the time step and making sure nothing changes. If you wanted to try a whole bunch of different spring free lengths, you could have a cell in here for the free length, and you could multiply out the things that we did in Newton's law to give you new values of these constants. So if I'd used a spring free length of 90, I would have had numbers different from 8.58 and 718.9. So you could automate that all in the spreadsheet with minimal modification, and that would make it a lot easier to change your spring free length. Okay, the final thing I'll bring to your attention is that when velocity goes to 0, the slope of the position curve should be 0, which means it should flatten out, which it does. Early on, the slope of the position curve is positive, and I have positive velocity. After 0.6 seconds, the position curve is going to acquire a negative slope, and I see a negative velocity. So all looks good with the world.